Hello guys, how are you doing today? Today we're gonna be continuing with the analysis of trusses, which is chapter 6. The last lecture, as you remember, we covered the method of the joints. We said, okay, if we have a truss like this, based on the same principle that we have always discussed, and we said if the structure is in equilibrium, every portion of the structure must be also in equilibrium. That means that I can go and take an analysis of each one of these elements, each one of these joints at these points, and that joint should be in equilibrium also, because we were working with joints. Basically what we were doing is particle equilibrium. So I'm going to isolate the joint B, like in this example. I'm going to put every single force that acts on that joint with the angles included, and because we are doing particle equilibrium in 2D in this particular case, then what happens is that I'm gonna have I can make use of two equations which are summation of forces in X and summation of forces in Y. So that means that I can have also a maximum of two unknown bars or forces in that joint, and we did I think a really comprehensive example in the method of the joints. We also covered zero force members last class, and we say that we have trusses like this, and suddenly you have this situation like this joint D. If you realize here this joint D, and we do summation, we isolate it and we do summation of forces in X, there's nothing in X, no force in X, just this bar. That means that bar should be zero, and hence that bar also should be zero. Those are zero force members. And I show you a really big example on zero force members, and also two rules. The first rule, which is this one, it says if you have a joint like this one or like this one with only two non-collinear elements, that means not only bars in the joint, but it could be bars or forces in that joint. But they have to be non-collinear and only two. That means that both of them are going to be zero. That's the way you're going to recognize them. Also, you have another rule which attain to this joint and this joint. And what happened here, the rule is if you have three elements, three forces or three bars, or forces and bar combination, two of them are collinear. Like you see, if you isolate the joint D, you have DE and DC. These are collinear, but DA is not collinear. And you don't have any other force applied or reaction support, then the one that is non-collinear is going to be a zero force member. That's the second rule for zero force members. Okay. That works perfectly and always work, method of the sections. Sometimes it takes a lot of time depending on what you want to do. So that's why we have another method, which is the method of the sections. I'm sorry, the method of the joints. We have now the method of the sections. The method of the section works basically based on the same principle. Part of the structure is the whole structure is in equilibrium. Part of the structure should be also in equilibrium. Now imagine that you have this truss, and I don't know, for any circumstance you want to only revise or review this particular bar here, that truss. If we apply the method of the joint, that means that I have to go either to this end or to this end, find the first joint with two unknown bars, calculate the reactions if I need to, and then I start moving from this joint to this joint to this to this to this to this to this up to I reach this joint, which is the bar that I want to calculate. Can I do that? Yes, definitely I can do that. Is there any other possibility of doing it faster and more rational way? Yes, it is. That's the method of the sections. That's what we're gonna do. And the method of the section consists in the same principle once again. I can make cuts and separate two parts of the structure, meaning this. let's say that I have this structure and I'm interested in calculating only this bar, or this, and this bar. So I can make a section here and separate both sides of the structure, as you can see here. This bar corresponds to the left side, this bar corresponds to the right side of the truss. Now look closely. This is the joint B, this is the joint G. So this force is going to be FBC, from B to C, from G to C, and from G to F. It doesn't matter the direction that I put the forces so far. Reason for that, remember that once I calculate the final result, if I get a negative value, that means that my assumption was incorrect, and I just have to flip the direction of the force. So you don't have to really care too much about it. It helps if you place the correct direction at once, but it doesn't make too much of a difference. The important part is, if you are assuming this force is going, leaving the joint, coming out of the joint, like we are assuming, which is tension, remember, in the other connected joint, which is the joint C, corresponding to the right part of the structure, it has to be also leaving the joint. You see that? Leaving the joint here, leaving the joint here, leaving the joint here, leaving the joint here. This part was assumed entering in the joint. Well, then it's going to be entering in the joint here, and this bar, we are saying, because we don't know it yet until we calculate it, that is subject to compression. Now, if you look closely, once again, we are cutting 3 bars. That doesn't mean that this is the only thing that you can do, cut 3 bars. But we are taking advantage, full advantage of what we are doing here. In the case of the joints, what we were doing actually was a particle equilibrium. In the case of a truss, method of the sections, what we are doing is we are analyzing a rigid body, the whole thing. Now we have an extra equation, which is summation of moments. That's why we can cut up to 3, we can have up to 3 unknown forces or unknown bars when we apply the method of the section. So we're going to have summation of forces, summation of moments, forces in X and Y, that means 2 equations, and summation of moments is the 3rd equation. And remember, we are only working in 2D for now. Now, the way you solve this, I'm saying 1, 2, 3 unknowns here. If I select this side, 1, 2, 3 unknown here. I have 3 equations, summation of forces in X, Y, and moment, and then I start the system. I set a system, summation of forces in X, summation of forces in Y, summation of moments, and I solve it. Now try to be smart when you do this, because if I say, let's say, let me do summation of forces in X as the first equation, then I'm going to have the X component of this plus the X component of this minus the X component of this equals 0. That's not going to give me anything. But let's say that I do summation of moments at this point. If I do can I do summation of moments at this point? Oh, that point is not part of the cut. I don't care. I can do summation of moments here. I can do summation of moments here, 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 here. Any point, because it has to be 0. I explained that to you tons of times. So if I do summation of moments here, my only unknown will be this one, and I can calculate it immediately. It will be this force multiplied by this distance minus this force multiplied times this distance equals 0. And once I have that, I can also make, or before that, summation of forces in Y in this section equals 0, because the only unknown in that point in Y is FGC, and once I have this and I have FGC, I do summation of forces in X and I can calculate FBC. That would be basically selecting what side to start is important, because imagine that we started in this side. How many unknowns do I have? I don't have 3, I have 1, 2, 3, 4, 5, and 6, because reactions are unknown also. Unless I take the whole structure and I calculate first the reactions. I can do that also. If I do that, there's no problem. I calculate the reactions, I know these, I can use this section, and I have 3 unknowns. But that requires extra work. Look at this. As shown, a cut is made through the members GH, BG, and BC. GH, GB, BC, and this is the cut. What part would you use? Well, this is basically the same example that we had before. If we use the left part, then I have to calculate first these reactions. I'm going to have 1, 2, 3 unknown bars, but I also have to calculate before the reactions in the whole structure. But if I use the right side, which is the correct answer, I only have 1, 2, and 3 unknowns. I don't have to do anything else. And I can start doing summation of moments here, calculate these, and then summation of moments here at the concurrent point, which is the joint between these two, and I calculate this one. And summation of forces in Y to calculate the next one. Okay. So in the method of the section, generally, and read this with caution because it says generally a cut passes through no more than, I say 3, right? Members in which the forces are unknown, but this is just general. There are some cases that you can make a cut and calculate even though you have more than 3 unknown. For instance, look at this value. Look at this here. It says, can you determine the force in ED? ED is this bar. By making the cut in the section AA. And there's no, there are 4 unknowns, or yes. Well, check this part. And let's work with the, let's say, the right hand side. I have 1, 2, 3, and 4 unknowns. But if I do summation of moments at this point, these 3 unknowns don't produce any moment here, and the only force acting in that summation is ED, which allowed me to calculate it immediately. What do I do after that? I can't continue with the sections. I have to go back to the joints and start. But the problem states only if I can calculate ED. Yes, you can do moment here after you do the section. You can do moment here and calculate ED. Okay, let's do an example. So this is an example that I'm going to show you now. And it's like, given these loads on the roof truss, calculate the forces in the members DE, DL, and ML. And let me go, let me use the dog camera for that. Okay, I'm gonna use the camera document for that. We have the, this is what we have actually. This is the problem, and in this problem, we have to calculate DE, DL, and ML. Well, it's pretty obvious here. If I have to calculate just these 3 bars, DE is this one, this one here, DL is this one, and ML is this one. That basically defines my section. I'm going to start and I'm going to make a section here. And I'm going to separate this in 2 parts. Now, if I do that, this is a pin, this is a roller. I'm going to have also 2 reactions here at the pin. I'm going to call this AY and this AX. And at the roller here, I'm going to have 1 reaction. I'm going to put it here, but you know it's acting at I at this point. This is IY. I'm going to have 1, 2, and 3 unknown forces or unknown bars in that cut, but I also have to calculate the reactions. So let's calculate the reactions before doing any other stuff. How do we calculate the reaction? Well, we can start by calculating summation of moments. Let's say at A equals 0, and I'm going to say this is positive. If that is correct, then I'm going to have summation of moments here. I'm going to have 12 times 4, and according to this convention, if I say this here is positive, then this one is going to rotate in the other direction, right? So now if I push this here, it's going to make rotate it in this direction, which is negative according to the right hand rule. So it's going to be negative 12 times 4. What about this one? Negative 12 times 8. Another 12. Negative 12 times 12. This other 12 times 16. These other 12, 4, 8, 12, 16, 20. This 6, 24. And then I have this reaction IY positive because now it's acting in this direction. IY times 24. This we didn't take it into account in the summation, but remember this one is passing through the point where I'm conducting the moment, the summation of the moment. So principle of transmissibility, I can pass it through the point. That means that force is not producing any rotation. The only thing that that force could be trying to produce is a translation, not the moment. So this is going to be equal 0. Once I solve for this, my reaction IY is going to be 36 kilonewton. If I do summation of moment, summation of forces in Y equals 0, then we're going to have that AY positive minus 6 minus 12, 1, 2, 2, 3, 4, 5, 12, 1, 2, 3, 4, 5, minus 6 plus IY equals 0. This is this one. So then AY is going to be also 36 kilonewtons. And I can do also summation of forces in X equals 0. I don't have any force in X, meaning this reaction is going to be 0. And as by doing this, I just wasted, I don't know, 2 minutes maybe of time. Is that important? Well, depending if you are in a test, it might be important. So you have to be smart when you do engineering, and at the level that you are up now, I think that you should start looking at this type of situation. What I'm referring to is this. You see that all the loads are symmetric, and you see that all the distances also are the same. The conditions of the support are basically the same. Now, if I have a horizontal force, it's different. But I have only vertical forces. Basically, the same conditions are for the support. So now imagine that you have just any type of element, any type of beam, and that beam is resting in 2 supports here. If I have one load only at the top of that beam here, that load is 100 pounds. This support is going to take 50, and this support is going to take 50. That makes sense. So when you have symmetry in the load and symmetry in the structure, like this one, this reaction and this reaction has to be the same. So I could do this just by saying, how many forces of 6 I have? 1, 2. 2 times 6, because I have 2 forces of 6. Negative, because it's going down. Okay, perfect. And then I have 1, 2, 3, 4, 5. Plus 5, negative, I mean. Negative 5 times 12. That's 12. That's 60, right? The total vertical load is 60. Negative 60 kilonewton. This 60 kilonewton are absorbed by this AY and this IY, which are the same. So each one of them, not 60, 72. I don't know why I say 60. 72 kilonewton. 60 is just this multiplication. 60 plus 12, 72. So that means that this 72 has to be taken by these 2 forces, which are the same. That means that AY equal IY equal 36 kilonewton. Directly. And you know what is sad? That I have had students doing this and getting different values for IY and AY and not even questioning their answers, not even trying to think, oh, why I'm having different values. That's sad. If you don't do this at once, okay, that's understandable. But if you come here and you don't even take the time to analyze that these two should be the same, then you're not grasping the concepts in statics. Okay, we calculated the reactions, and we're going to make a section here. When we do that, we are going to have basically this. I made a section here. This is this force 6, this is 12, this is 12, distance of 4, 4, and this is my joint L at this point. And my three forces are DE, this is DE, DL, this is DL, and ML, this is ML. In this particular problem, I am assuming that DE is entering in the joint like this, DL is entering in the joint also like that, and ML is leaving the joint. Do I have to do that? Do you have to take that assumption? No, you don't have. As a matter of fact, most of the textbooks they assume all the time leaving the joint. That means in tension. So in that way, if you get a negative sign, you know it's in compression immediately. But it doesn't matter the way you assume it. Remember, at the end, the sign is gonna tell me if my assumption was correct or not. Okay, now. Let me see, focus is correct. How are we going to proceed? How are we going to calculate this? Well, this is the 36, by the way, okay? And remember to include everything and all the forces that are included in that section. If you miss one of these forces or reactions, then you're going to have the problem is going to be wrong. How do you start solving this problem? Well, it's easy. If I do summation of moments at D, this force and this force are not producing moment whatsoever with respect to the point D. The only forces producing moment is force ML, this 12, this 6, and this reaction. So let's do that. But in order to do that, I need to know how much is this height from here to here. I said it's 5, and I say it's 4, and I say it's 3, yeah, and this is 6. How would I say that? Well, remember the only information that you have, the only data that you have is this is 6, and this is 3. But this is equally spaced. What is the difference between 6 and 3? It's 3, right? If this is equal space, this has to be 1, this has to be 1, and this has to be 1. So this has to be 3, 4, 5, 6. If you want, you just can calculate the angle because you have this part, then you have this part, and you have this part. This distance should be 12, 4, 8, 12, and this height here should be 6 minus 3, 3. So if you want to calculate how much are each one of these, and this is 4, each one of them is 4, you can make a triangle ratio and say, I don't know, 12 is up to 3, as 4 is up to y, and from here you can solve y equal 1. So you know this y is actually this distance from here to here, plus 3, that would be 4. If you do the same for this one, then you can say 12 is at 3 as 8, because now we have 4 plus 4, 8 is up to y, and y will be equal to 2. So this height here from here to here is 2 plus 3 is 5. That's exactly what I did here, but I did it without doing the ratio. Actually, yes, you do the ratio, but you do it in your mind, so you don't have to write it up. So if I'm going to do summation of moments at the point D equals 0, and I'm going to assume that this is positive, then let's start from this corner. You're going to have this force of 36 times the horizontal distance between these 2 points is 8, and this is going in this direction, which is going to be negative. 36 times 8. Now you have this positive 6 times 8, because 6 is the force, 8 is the horizontal distance here, 8. Now you have again positive 12 times 4, And remember, this force doesn't produce anything because I'm doing it on top of that force, exactly at that point. But this is producing. This is producing a positive moment. Remember, if I pin it here, rotation is going to happen in this direction. And this distance is 5, and this force is force ml. So plus 5 times force ml equal 0. Then 6 times 8, 6 times 4, 6 times 8. So that means that this is basically 30 times 8, 240, 240 negative 48 divided by 5. Yeah. So the force ml is equal to 38.4 kilonewton. We assume the force ml like leaving the joint, and the result is positive, so that means that that force is in tension. Now we have to calculate, let's say, the force dl. How do you calculate the force dl? I could do summation of forces in x and y, but if I do summation of forces in x, I'm going to have this, which I know, but I'm going to have these two. If I do summation of forces in y, I'm going to have the y component here and the y component here. So once again, let's be smart. What if I do summation of moments at this point? If I do summation of moments at this point, then the only force producing moment is this. And when I say let's be smart, let's be a little bit even smarter. Because I can put it here, but if I put it at this point, then I'm going to have two components. I'm going to get this force. I'm going to apply the principle of transmissibility. I'm going to put it exactly on top of L. I can do that. We have done it before. If I do that, the horizontal component of this force is not going to produce any moment because it's passing exactly through the point L, the vertical one. But the horizontal one is the only one producing moment. This force, remember, is force dE. And this is the horizontal component of the force dE. So this force is not going to produce moment with respect to the point L. In order to calculate this, I need this angle, because it's going to be FDE, cosine of the angle, or I can just say, okay, wait a second, I know this is 4 because I said it before, right? The angle. I know this is 4, I know this is 1, so I have this triangle. If this is 4 and this is 1, that's going to give me the slope. And this is going to be the square root of 4 squared plus 1 squared, which is 17. So I can say that this component, instead of using the angle, you can use the angle, calculate this angle if you want to. But I can say that the cosine of this is 4 divided by square root of 17. And I can use it like that. Personally, I like using these type of relations. So let's do that. Let's do summation of moments at L. And let's start with this value. The first one is going to be 36 times. Now if I'm here, the distance is going to be 4 plus 4 plus 4 is 12. And it's going to be negative according to my convention because it's rotating in this way. And that way, according to this, is going to be negative. Plus 6 times the same 12, 4, 8, plus 12 times 8. Now this is producing because it's with respect to this point. So it's going to be plus 12 times 4. This is not producing moment, this is not producing moment, but the horizontal component is producing moment. Remember, the horizontal component is, first of all, this is going to be positive, and it's going to be FDE multiplied by 4 and divided by the square root of 17. And that has to be 0. And of course this has to be multiplied also by the distance, because that's this. What is the distance between this point and this point? This distance, 6. That's 6. When you solve this, you get that FDE is equal to 37.11 kilonewton. The value that I got for this, that's a positive value, meaning the reaction, the force, it was placed in the correct direction, and because it's entering at the joint, and I'm assuming entering at the joint, that force is in compression. Finally, after that, I can do either summation of forces in X or summation of forces in Y, and I can calculate my last unknown, which is dl. So I can do summation of forces in X equals 0. I could do it either way in Y also. So if it's in X, I'm going to have this force ML, which I already calculated before, 38.4 positive. This force is going to the left, and that force is going to be negative 37.11, which is the value of dE multiplied by 4 divided by the square root of 17. That's the horizontal component of this force. And I can do the same thing for this one, because I know this height here is 5, this distance is 4. Then I'm going to have a triangle like this, 5, 4. I can calculate this angle if I want to, or I can say that this distance here is the square root of 25 plus 16, this is square plus this is square, and that's 41. So the horizontal component of the force dl, first of all, is going to be negative, acting in this direction, negative FDL times this divided by this, and that's 0. Once I solve this, FDL is going to be equal to 3.84 kilonewton. And once again, the value obtained here is positive. That means that the convention that we assume with this force dl entering in the joint D was correct. That means this is in compression. Don't get confused, because now you can think that this force is entering in the joint D, L, and this force is leaving the joint L. No, L is not the joint. L, in this the diagram that we are doing, remember we made a section, and the section was here. So L is not part of this substructure that we calculated. L is just one point in the plane. What is important is that the force is entering in this joint, and is entering in this joint. If I'm going to transfer that force to this other joint, it will be in this way, and it will be going out of that way. But that's not what we are doing, at least not now. This is a nice example. I'm going to assign some more as a homework. Most probably today I will be doing that. But this is a nice example of trusses. Please go and practice trusses, because you're going to need trusses a lot. And of course that's going to be a big chunk of the test, the second test that we're going to have. That was part of what I had for today. Now also, one of the other, oh, this is full of other presentations. Let me see. Yeah, the other part that I wanted to discuss with you today is a little bit of what is called internal forces. And if I was in the classroom, I would be asking you right now, have you heard about internal forces before? Yes, you have, of course. When? Don't tell me 3 weeks ago, don't tell me last semester, tell me 30 seconds ago. How come 30 seconds ago? Because when we were solving the problem of the truss, all those forces in the bars are internal forces. They are happening internally in the structure, not externally in the structure. So those are internal forces. We're going to use the method of the sections here, but not for trusses in this case. It's for any type of structure, any general structure. We can make sections and calculate those internal forces. And as you can see, this is, for example, a beam in a bridge. You see, this beam is usually thicker at the supports. There has to be a reason for that. Of course, there is a reason. The reason for that is because there is an internal force here that is big, and there is also a moment happening here, which we're going to discuss later, a negative moment. And that's why they made those taper beams there. Now, have you seen these type of situations also? Haven't you wondered why this is thicker at the base than here, for example? Or this type of situation, why do this frame needs this extra structure at this part? Those are some stuff that intuitively you know, but now we're gonna learn why that happened in reality. What is the responsible for those modifications or alterations there? When you are going to design now, remember there is a big difference, and we discussed that difference between analysis and design. When we are designing, or we're analyzing means I'm going to have the geometry, I'm going to have everything, I'm going to have all the loads applied to one structure, and I'm going to have the dimensions of that structure, the material of that structure, those elements, and I'm going to just verify that that particular element is going to satisfy the criteria that I wanted for building it. What is going to happen? If it's going to be a classroom, it's going to be sufficient to withstand all the loads corresponding to a classroom. That was the analysis. Now the design is the opposite, kind of. I have the forces, but then I'm going to design, and I'm going to calculate, and I'm going to come up with the material and the cross-sectional area of the element, the shape of the element. In order to do that, I have to find the internal forces in each one of those internally, in those points in that structure. I'm not talking about point A, B, or D, because when I design everything, so I need those internal values everywhere also in that beam or in that structure. I'm talking about beam, but it doesn't have to be a beam. So let me switch again to camera document here really quick, so we can talk about this. We just did a case in the truss, and the truss was something like this. I don't even want to know exactly how the truss was, but let's say that the truss was like that, reaction, and force there. We said that due to the nature of the truss and how these are smooth beams and all the forces are applied only at the joints, if I make a section or I analyze a joint or I check any of the points, basically what we have is that in that truss internally all the elements are going to be subject to internal forces, and those internal forces are going to be only either tension or compression. Tension or compression, that's it, nothing else. But that happens only in trusses, or mainly in trusses. Why? Because all the constraints that we have, no forces along the elements, just at the joints, smooth beams, that makes them like kind of a two force member, and because of that the forces are only tension and compression. Now if I have a beam, any type of beam, I'm gonna put a fixed support here, I'm gonna put this beam subject to forces, to moments. Same principle apply. This beam is gonna have some reactions here, here, let's say, and here. Those, because it's a fixed support, I have 3, right? Y, X, and moment. But if I make a section here, if the whole structure is in equilibrium, once again, every part of that structure should be in equilibrium. So this part and this part should be in equilibrium. The only way these two parts are in equilibrium is if at this part, this end, you have some internal forces acting on that part. And in this part you have also some internal forces acting in this part. And these internal forces are the ones that are going to keep this part in equilibrium. My goal is to determine those internal forces, because with those internal forces is that we are going to basically design that element. This force, the first one, if you have a structure like this and you make a section in this part, the first internal force that appears here is called V, and that's shear force. Shear because it tries to cut it in two parts, separate two parts like this. This other force acting here, this acts perpendicular to the cross-sectional area. This one, this force, is called axial. I'm sorry, I just make a pause in the recording because I had to sneeze. So, this force is called either axial force or normal force also. Normal force is more like physics. I like more the term axial because it's more like engineering. Axial force. And also you have a moment. Which in this case, that moment is a bending moment, not a torque. I know that torque moment, everybody told you that it was the same thing, and yes, it is kind of the same. But I told you also that when you refer to moment, usually you refer to bending moment, moment, bending moment. And when you refer to torque, you refer to the other direction, the torque around the axis. So moment, axial, and shear. And at the other end also, if this is one end, and this has a load here, and this has the other reactions, I'm just going to copy them like that. And at the other end, same forces appear, but of course, action-reaction has to be opposite to this one. So this is shear, this is axial, and this is moment. By the way, this is the accepted convention for the internal forces positive directions. At this end, if you make the section at this end, you're going to have the shear acting this way is going to be considered positive shear. That doesn't mean that when you do summation of forces, you're going to say this is positive. No, that means that I'm going to put it like that, and when I do summation of forces, I choose whatever direction, positive or negative, I want to. But if the result, by putting it like that, is positive, that's going to be a positive force. I know that sounds weird, but I'm going to explain you now how to do it. One of the things that I told you also was that you need these forces. Well, maybe the most critical ones are when they are going to be bigger within the beam, but also we need it everywhere. So we have to calculate here, everywhere, all those forces. That means a lot of work, but we don't do it like that. We don't do a section in every single point. That's why we enter in the next topic which are shear, axial shear and moment diagrams. That's what we do. Let's do an example so I can show you how this method works, but basically you know how it works. Of course, now we are dealing with rigid body equilibrium, or again, method of the sections, so I can have maximum of 3 unknowns in order to solve it, because I'm going to have also a maximum of 3 equations. Let's do one example, and I'm going to do a beam. This beam, I have a simple support here, a pin support, and a roller at this end, and it has a moment applied at this point of 40 kip per foot, and I have one force applied here of 8 kip. I have one point, this is not a hinge, this is just a point that I'm showing on that beam, and the distances are gonna be 8 feet here, 8 feet here, and 8 feet here. And the problem asks calculate the internal forces What are the internal forces? Axial, shear, and moment. Where? At the point C, at the point D. That's what we have to do. So we have to calculate the internal forces, axial shear and moment at C and D. How are we going to do this? First thing first. This is a pin. I'm going to have a Y, AX, and here I'm going to have BY. Second, I have to calculate those values, because otherwise I'm not going to be able to calculate any internal reaction, at least not in this particular problem. So let's do summation of moments at A equals 0 in the whole structure without doing any section before. Summation of moments here, then I'm going to have this 8 times 8, and this is going to be negative according to this, plus this 40. Remember, this is a moment already. I don't have to multiply by any distance because the moment already happened. Plus this force By times 24 equals 0. If I solve that, I'm going to have this is 64 negative plus 40, that's negative 24, so negative 24. So By is going to be 1. Kip. Remember, kip, kilopound, 1,000 pounds. Summation of forces in Y equals 0. AY minus 8 plus 1 equals 0. AY equals 7 kip. Summation of forces in X equals 0. AX equals 0. Okay, this is nothing different than we have done before. Now I'm going to start, because it's the easiest part, I'm going to start with the point D. I'm going to say, okay, let's calculate our forces at the point D. Basically what this is telling me is that I have to make a section at D. So I'm going to make a section at D like that. I can use either side for the time being. I don't want to confuse you even more than you are so far. So I'm going to use the left hand side And remember, whenever you do a section, you bring everything that that section has with it. The only thing that I'm not putting is this reaction AX because it's 0. So I'm not gonna even copy it. This is 8 feet. And this is, let's say, 8 feet or almost 8 feet because, yeah, it's 8 feet because I'm making the cut exactly at the point D. So let's make it 8 feet. And this is the point D, this is the point A. Remember, we said that here we have to have a set of internal forces, and those internal forces are going to be a shear in D. Notice, once again, I'm putting the shear in the accepted convention for positive, which is this one. Moment at D, and axial at D. What do I do? The same thing that we have done before, summation of forces, summation of moments. Summation of forces in X equals 0. That implies that AD is 0 because I don't have any other force. Of course, if this is inclined, then I have to include it, but it's not inclined, so I don't have any horizontal component. This is 0. Summation of forces in Y equals 0. I have 7 kip minus 8 kip minus, I know this, I said this is positive, but anyway, when I do summation of forces, I'm assuming this is positive. It doesn't matter. I can do that or otherwise. It doesn't matter. The reason for that is because this is equal to 0, and if I multiply the whole equation by -1, it's just going to flip the direction, so it's the same. But the important part is this. BD, when I do that, it's going to be what? 7 minus 8 is -1, correct? -1. So I'm going to have -1, but when I pass this to the other side positive, this is going to be negative here, so it's going to be -1 keep. -1. That's important. Why? Because that is telling me that at D, the internal force is going to be -1. I assume it in the positive accepted convention, and I got a negative value. Yes, that could imply that it goes in the other direction also, as we say. But when dealing with internal forces, I'm interested in this value here, the negative value over there. Okay? Now, if I do summation of moments, where would you do it? Actually, anywhere. Let's do it at D. Why am I doing this? Because I want to calculate that MD, the moment at D. If I do summation of moments at D equals 0, then I'm going to have that this is positive 7 times 16 this way, and that's negative according to this, plus 8 times 8 plus MD equals 0. Seven times 16 plus 8 times 8 plus MD equals 0. 7 times 16 is 104. No. 112. This is 64. I didn't really calculate. I'm going to do it really quick here. I don't know if I have that answer. Yes, I do have that answer. 356. Let me calculate it really quick. Calculator. So this is gonna be 7 times 16 minus 64. That's 48. 48 positive. So MD is gonna be 48. positive, and that's the value that I'm looking for. What for we use this? What for we use this? For designing the element, as I told you. Let me really quick go through this and tell you what does that mean. Imagine that you have, I don't know, once again, a reinforced concrete beam. You have a beam, and I know you know what is a reinforced concrete beam because we have talked about that in several occasions before. You're gonna have 1, 2, or whatever rebars here embedded in the concrete, those rebars like that. Now if you have the beam like this and you apply force, this is a support, this is a support, and you apply a force coming down, that beam is gonna try basically to bend in this direction. So that beam is gonna do this. If it's gonna bend, this is the moment that we are showing there. The moment acting in this direction. The moment acting in this direction is producing, as you know, also in the top part compression and in the bottom part of the fibers tension. Now if this is concrete, the concrete is not very good for resisting tension, but it's very good for resisting compression. It's not that it's bad, that in tension it takes about 10% of the compression value. So this part is gonna be cracks in the structure, and the structure can collapse. That's why you supply this area of tension, you supply it with the steel rebars to absorb that. And this longitudinal steel is calculated with the moment that we have in that diagram. A positive moment indicates compression tension. The moment that we just calculated here is a positive moment at that point. That means that if this is a reinforced concrete beam, I'm gonna have rebars placed on the bottom part. Now if you have a negative moment indicates this, compression and tension. So whenever you have a negative moment, if this is reinforced concrete, which is it's a material that is not isotropic, the concrete, because it varies the tension and compression. So that means that rebars are going to be required on the top, whatever the tension is. That's why you use the moment in that particular example. Now you have I'm pretty sure that you have always also seen that whenever you have a concrete beam like that, you also have some structures that come like this, like bracing the whole rebars together, all the rebars like that. Those are called stirrups. Those stirrups are calculated with this value, with the shear. And of course you will see that later. Also the thickness of the structure is calculated with the stirrups. That's why now when you have the steel bridge like that, and these are the supports, that's why this part is bigger, because at the supports the reaction is going to produce a bigger shear than at the center. That's why this part should be thicker than that, and also for the moment at that point. Okay, that's the first part of the problem. But the second part of the problem, it says at the point C. Internal force at the point C, and you're going to say, oh, but we do the same thing. Well, basically, yes, you can do the same thing, but it's not the same. You have to be really careful when you do this type of situation, you have this type of situation, because then you say at the point C, but at the point C you have at the point C you have a force of 8. Keep acting. Should I include the force or should I don't include the force? That's the question. And I wish I had you in front of me so you can ask that question. Because if you say the answer is yes, you're correct. But if you say the answer is no, you are also correct. Because what happened is a little bit, and a little bit in math, we talk about differentials, right? So a little before the point C, you don't have any force. And a little after the point C, you have the full force acting. That means that in that point, it's going to be a sudden change in vertical force at that point. And the only way that you have, or we have, to show that is doing it before and doing it after the point. So let's do that. Usually the problems tells you, I'm now talking academic problems because of course in real life you have to do it in the way that I told you, but usually the problem tells you do it before the point C, or the force is applied exactly after the point C or exactly before the point C. So you have, you know, if they wanted you to include it or not to include it. This problem in particular say at the point C, so we're gonna do it before and after. What we have to do, the first case, we have a force here. I'm doing a section just before the point C. This is 7 kip. If it's exactly before the point C, then I'm not going to include the force of 8. This is going to be 8 minus a differential, so that means 8. But I'm going to have also my shear at C. And I'm going to have my moment also at C. And I should have the axial also at that point. But I'm not going to even put the axial because it's 0. I don't have any other force there. And I do the same thing. I do summation of forces in Y equals 0. Then I have BC equals 7 kip. And I do summation of moments at C equals 0. Then I have negative 7 times 8, negative 7 times 8 plus MC equals 0, so MC equals 56. Fit kip or kip fit. That was before load. Now let's do the other part, after load. When doing this after the load, then I have definitely to include that force 8 on that point. So I'm going to do it. I'm going to include that force here. 7, 8. This is also 8 feet because one differential before, one differential after is the same thing. This is going to be my shear at C. This is going to be my moment at C. If I do summation of forces in Y equals 0, then I get 7 kip minus 8 kip minus VC equals 0. So VC is negative 1 kip. And if I do summation of moments at C equals 0, then you get that negative 7 times 8 plus MC equals 0, so MC equals 56 kip feet. And let's stop here just a second. Look what happened. We calculated before the load the internal forces and after the load. The load meaning that 8 kip at the point C. Look the value for the, I'm going to put that arrow like this because somebody's going to ask me, why is pointing to the left? Look at the value for VC here and look at the value for VC here. It changed dramatically from 7 to negative 1. And that makes sense because it's a vertical force in this case. What is the distance between 7 and negative 1? The distance, remember the numerical, the number line? Negative 1 is here, 7 is here, the distance is 8, which is the value of the force. So in that part, whenever you have a concentrated shear load acting, that's going to produce a sudden change in the point regarding the shear. But let's look at the moment. Look at this moment and look at this moment. The same. Didn't matter at all. It didn't affect the internal moment at that point, the location of the force. When we do the diagrams, which is going to be the next chapter, when doing the diagrams, we have those values, and what is going to happen is something like this. I know you don't know exactly what I'm talking about right now, but I want to really quick build a diagram. Don't care too much if you don't understand the diagram, but my idea is to show you what happens in that point. I'm gonna build my shear diagram here, and I'm gonna build a moment diagram here. This is my force. My force is 7 kip, and this force is 1 kip. 7 kip, my shear diagram is gonna jump. I'm gonna explain you that later. It's gonna be constant here, and this is 7. I find this 8 going down, so this is gonna be -1. And from here it's gonna come here, and I have this force going up, which is 1, and it reaches 0. This is the value of C before, the one that you just calculated, 7. You see it there? And the -1 is the value after the point C, 7, -1. Now, when looking at the moment here is going to be 56, and it's going to go up to 40, and it's going to close at 0 here also. But at the point that we calculate the moment here, 56 before and after is the same. It didn't change at all. And that's exactly the same values that we are getting by doing the sections. 56 and 56 here. At the point D, which was this point here, we calculated also the internal force at that point, and the internal force at that point, the shear, was -1 at D. That's the value that I have on the diagram. And the moment was 48. That means that the moment here is going to be 48 at this point. Now, with all these diagrams that I proceed and I do the design of the member, of the element. My suggestion to you is now go practice a lot. I'm going to assign a homework on this, and also now probably my SI leader is gonna, or my assistant is gonna continue with this lecture and show you some examples of what to do in class. So I see you next class, guys. I hope you enjoy it, and please go and watch it. Go and watch it because you really need to watch it. I'm not gonna go over this again. So watch it and learn it and practice in the book. Have a nice weekend.